Good evening to all the people who have joined in. So, we will be doing the third part of the energy materials lecture series, and we will be covering a little bit of the batteries and supercapacitors. We have already done two lectures previously, and this is the third lecture of the series. So, today, what we will cover is cell characterization. If you remember, in the last class, we had talked about cyclic voltammetry, and we have also talked about the charging and discharging of the battery cycles. We were talking about cell characterization, means the coin cell characterization of the batteries. So today, in continuation with the cell characterization techniques, we'll be covering impedance spectroscopy. Then I'll talk a little bit about what you mean by a life of a battery or battery life. Then we will cover supercapacitors, that is electrochemical double layer capacitors, pseudocapacitors, and hybrid capacitors. And then we will talk about the concept of fuel cells. So with this, we will complete basically our entire energy storage materials. So coming to what is electrochemical impedance spectroscopy, and it's a very important technique when you're actually finding out the dynamic variation which is happening when you're having a coin cell. So if you remember, this coin cell is nothing. It is basically the single cells, and these cells, when they are connected in series and parallel, what you get is a battery setup. So EIS is a very good non-destructive route to in situ analysis of the dynamic processes which is occurring inside a battery. So whatever process in the process in the battery includes that. If you're talking about the lithium-ion battery, from the cathode to the anode, there is movement of the lithium ions, and then again back as you are charging and discharging the battery. So what is exactly happening in situ inside that particular cell? Electrochemical impedance spectroscopy gives us a very good view of that, and it is a non-destructive route also. Many times you will see that people are using XPS to find out what is happening, or XRD to find out what is happening inside the cell. But most of the time what happens is it is done XC2. That is basically you are actually charging or discharging the battery at a particular voltage, you are stopping it. Then you are disassembling the particular cell, you're taking out the material, and then you are checking for it. So in that process, you are actually destructing the cell. But electrochemical impedance spectroscopy, it offers a non-destructive route to the in situ analysis of these dynamic processes which are occurring inside the battery. So what it does is it provides a considerable amount of information in a relatively short space of time, and it preserves, in the meantime, it doesn't disintegrate the battery, it preserves the integrity of the battery. So what you do in EIS, a small alternating current signal is applied over a wide frequency range, and its response is then measured. So EIS is particularly sensitive to systems that contain several impedance elements, including bulk components and interfaces, which makes it well suited to study a multi-component device such as battery. So in batteries, when you say bulk components, you have the electrodes. In interfaces, you have the electrolyte electrode interface. So all the different processes which goes on in the bulk as well as in the interfaces, this can be actually separated and studied very nicely using impedance spectroscopy, as we will see in the coming few slides. So one thing you have to remember is that different components and processes within a cell, that's a battery cell, it operates on different time scales. So that is, they have different time constants, and then they can be separated in the frequency domain using this electrochemical impedance spectroscopy. So when we talk about electrochemical impedance spectroscopy, on the right hand side, if you see, this is how your electrochemical impedance spectra looks like. And to get the necessary information of what is happening inside the cell, you have to actually model an equivalent circuit, which is shown on the top, this equivalent circuit. So whatever you see over here is basically what you will see if you run this particular circuit, and this is the electrochemical impedance spectra you will get. So experimentally what you obtain is this, and then you model and you find out the equivalent circuit which is generated, and from this you can give an idea about the processes which is happening inside the battery when you are charging and discharging it. So now you have to understand that whenever a battery is functioning or a cell is functioning, there are a lot of degradation mechanism which is happening in that rechargeable battery. So you can have electrolyte decomposition. So in that case, what you will see, there is loss of alkali metal, there is deterioration of the ionic transport. And at the end, the result is that you will see a fading of the capacity of the battery, and there is a rise in the impedance. Okay, then you can have a solid electrolyte interface formation, as I had discussed in the previous lectures. The same happens when you are having a solid electrolyte interface forming. What it is doing, it is actually decomposing the electrolyte decomposition is taking place, and a part of your lithium ion is actually getting lost in the formation of that SEI. So there is loss of alkali metal. Again, there is a deterioration in the ionic transport. So what you will see is a capacity fade and there is an impedance rise. Similarly, with binder decay also the same thing. With particle contact loss also you will find capacity fade and impedance rise. Whereas when you have a cracking of the particle, there will be loss of alkali metal and loss of active electrode material. So what you will see is a capacity fade, metal plating, transition metal dissolution, structural disordering or unfavorable phase transitions if you find. If there is a change in the porosity, in all these cases, you will find different kinds of effect as I've listed out over here. In case of the structural disordering or unfavorable phase transitions, you will find a loss of active electrode material, and again you will give rise to capacity fade. Now, there are certain things which can happen in the electrode surface, like there can be a change in porosity. So as your discharging or cycle proceed, what happens is you might see in the electrode surface there is a change in the porosity. So immediately there is going to be a decrease or a deterioration in the ionic transport, and immediately you will find a rise in the impedance. Similarly, you can have a decrease in the electrode surface area. There can be that, what is happening is with the charging and discharging, gradually that electrode surface, whatever is there more and more agglomeration is happening of the particles. So there is a decrease in the electrode surface area. Or else your lithium is going and sitting into the anode area and it is not coming back. So there is a decrease in the electrode surface area. If this happens, then again there is going to be a deterioration of ionic transport. You will find a rise in the impedance. Then what can happen is oxidation of conductive additives. That can also happen. So if you have that, then also there is going to be a deterioration of ionic transport. There is going to be a concomitant impedance rise. Then you can have a current collector corrosion. That is also possible. Your current collectors are made of copper or they are made of aluminium in case of sodium-ion battery. In case of your lithium-ion battery, it is made up of copper. So you can have a current collector corrosion happening because of the various reactions which are taking place during charging and discharging of a lithium-ion battery. And what you will see, there is a deterioration of ionic transport, and that can also give rise to a rise in the impedance. So whenever you are checking the electrochemical impedance spectra, it is actually showing you the health of your battery. What is happening when the charging and discharging is occurring in your particular cell. So now coming to understanding what exactly your electrochemical impedance spectra tells you, first you have to refresh a little bit of your memory. So what is this impedance? We normally heard about resistance, right? Everybody has heard about resistance. So Ohm's law defines resistance in terms of ratio between the voltage E and the current I. So what is R? That is the resistance is E by I. Now this relationship is limited to only one circuit element, which is the ideal resistor. So now an ideal resistor, it has several simplifying properties. What is that? The first is that it follows Ohm's law at all current and voltage levels. Then its resistance value is independent of the frequency. You can change the frequency, but the resistance is not going to change. And AC current and voltage signals through a resistor, which is the ideal resistor, they are in phase with each other. They are never out of phase or out of sync with each other. So they are in phase with each other. So this is when we talk about the ideal resistor and the resistance which is generated by it. But what happens in the real world? The circuit elements which we have in the real world, they exhibit much more complex behavior. So now instead of resistance, we call it as an impedance, which is a more general circuit parameter. So like resistance, impedance is a measure of the ability of a circuit to resist the flow of electric current. But unlike resistance, impedance is not limited by the simplifying properties or the simple properties which I discussed in the previous slide. What happens? Electrochemical impedance is usually measured by applying an AC potential to an electrochemical cell and measuring the current through the cell. So what is happening? You are applying an AC potential, a sinusoidal potential wave to an electrochemical cell, and you are measuring the current due to that application of that particular AC potential. So now what we do is we are applying a sinusoidal potential excitation. The response to the potential is going to be an AC current or alternating current signal containing the excitation frequency and its harmonics. And the current signal can be analyzed as a sum of the sinusoidal functions. So it becomes a Fourier series. So electrochemical impedance is normally measured using a small excitation signal. The reason is what was just discussed in this previous one. So instead of having a complicated Fourier series, what you have over here, that when you are having a very small excitation signal, you have a cell's response which is pseudo-linear. So what happens if it is pseudo-linear? So in a linear or a pseudo-linear system, the current response to a sinusoidal potential will be a sinusoid at the same frequency, but it is going to be shifted in phase. So you'll find a phase shift, but you don't have, this entire harmonics and, the entire Fourier series coming. So your analysis, it becomes a little more easier. So when we talk about sinusoidal excitation signal and what you're getting in return, so this is how it looks like. So you are having an excitation signal expressed as a function of time over here. This is your potential versus time, you see. And this is given in this particular form. It is Et is equal to E0 cos omega t. Where what is Et? It is potential at the time t. E0 is the amplitude of the signal, whatever you're having. Omega is the radial frequency. And the relation between this and your frequency, which is expressed in hertz, is given below. Omega is equal to 2 pi f. So now this is what you are getting. This is the excitation signal. But when you are getting the current which is coming out after applying this particular potential or excitation, sinusoidal excitation signal or the potential signal, you find the current which comes. It is also sinusoidal in nature, but it shows a phase shift. You can see this phase shift over here. So here it was starting like this and here it is coming. So this is the phase shift what you see whenever you are seeing the current. So how do you measure this impedance? So a frequency response analyzer, this is the thing which is typically used in combination with the electrochemical interface. So what you have over here is your battery and how you are measuring the impedance. The electrochemical interface applies this particular electrochemical interface. It is going to apply a constant voltage or a constant current. And this particular frequency response analyzer is going to superimpose a alternating current signal. So a multiplexer connects this FRA to the battery test system. So battery is connected using 4 wires, as you can see over here. 2 are used for current flow, that is one is here, the other is here, and the 2 are used for cell potential. So the FRA outputs a signal to the cell via the counter electrode, which is I minus, and the signal is returned through the working electrode, which is I plus over here. It also connects to a pair of reference electrode points, that is V plus and V minus, to measure the voltage across the cell. So the FRA, that is the frequency response analyzer, it applies a small AC signal, usually in the range of millihertz to megahertz, and measures the response whatever is generated. So now this EIS, it can either be used either in the potentiostatic or the galvanostatic form. So you can have either a constant voltage or you can have a constant current. So these are the two different modes you can have. Either you can have a constant voltage or you can have a constant current mode. So the potentiostatic mode, where a voltage is applied at each frequency and the resultant current is measured, this is most common. The current responds at the same frequency as the applied voltage, but as I discussed earlier, it may be shifted in phase. So in order to ensure a steady state, the EIS usually is carried out with a small potentiostatic signal amplitude of 10 millivolt, so that the cell response what you get is pseudo-linear. So that's why you have to apply a very small potentiostatic signal amplitude. Now, if the system is non-linear, what is going to happen? The response contains harmonics of this input signal frequency. So, what you have to do is, if you have to really perform a EIS accurately on a cell during cycling, you must have a rest or an open circuit voltage period. This is often applied at first, so the cell voltage does not vary significantly during the measurements. Similarly, once you have done that measurement, you have to have an additional rest period on open circuit. And this is implemented following the impedance scan to allow the cell to recover from any changes that occur during the EIS run, prior to continuing with constant current, constant voltage cycle. So please remember, in short, what it means is that whenever you are putting in that particular signal, before that you need to have a rest phase. Again, after that also you have to give a rest phase, so that this entire cell, it comes back to its rest phase, and again you can go on applying this small AC signal and seeing that how your current is getting generated. So this is how basically the measurement of impedance is generally done. So now coming into the details of it. So as I discussed in the previous slide, electrochemical impedance is usually measured by applying an AC potential to an electrochemical cell, and then you are measuring the current through the cell. So assume that we apply a sinusoidal potential excitation. The response to this potential is a AC current signal. As you can see, I have applied a sinusoidal potential excitation. What I get is another AC current signal. And this current signal can be analyzed as a sum of sinusoidal functions, which is a Fourier series. So electrochemical impedance is normally measured using a small excitation signal. So this is again, as I said, the cell's response should be pseudo-linear. And then what is going to happen is in the current response to a sinusoidal potential will be sinusoid at the same frequency, but then again it is shifted in phase. So please remember, to get this, what you have to apply is a small excitation signal. So the excitation signal expressed as a function of time, this is the form of that. Et is equal to E0 sine omega t, and this omega is nothing but 2 pi f. So the response what you get is going to be It is equal to I0 sine omega t plus phi, and this phi is nothing but, which is the phase shift whatever you see. So what you get over here right now is an expression analog to Ohm's law, which is going to allow us to calculate the impedance of the system. This impedance is given as Zt, which is Et by It, E0 sine omega t by I0 sine omega t plus phi. So ultimately what you have over here is a Z0 sine omega t by sine omega t plus phi. So the impedance is therefore expressed in terms of a magnitude Z0 and a phase shift phi. So now you have Euler's relationship. If you remember, exponential j phi is equal to cos phi plus j sine phi, where this phi is a real number and j is imaginary unit. So it is possible to express the impedance as a complex function because we are having Euler's relationship over here. So the potential and current response are described as Et is equal to E0 exponential j omega t, and It is I0 exponential j omega t minus j phi. So impedance is then represented as a complex number. So this Zt is nothing but Z0 cos phi plus j sine phi. So when you look into the slides later on, it will become much more easier if you are solving it out on a paper. So impedance, we will write something like this. So this is nothing but Z0 cos phi plus j sine phi. So it is Z prime plus j Z double prime, where this j is nothing but root over minus 1. So what we can say is that generated impedance spectrum, it has a resistive and it also has a reactive component. The resistance is made up of combination of this electronic and ionic resistances. And the most common form of plotting impedance data is a Z star complex plane plot of Z double prime against Z single prime on linear scales, and this is also known as the Nyquist plots. Presenting data in this way displays the resistance along the real or the x-axis and the reactance including capacitance along the imaginary y-axis. All whatever I discussed in this particular slide will become more clear as we progress through the lecture. So what we said is basically this z omega is nothing but z0 cos phi plus j sine phi. So now this expression z omega is composed of a real and an imaginary part. So this real part is basically on the x-axis, the imaginary part is on the y-axis, and this plot, the plot what you see over here is known as a Nyquist plot. So in this plot, this y-axis is negative, and each point on this Nyquist plot now is the impedance z at any one frequency. So please remember, every point over here is the impedance what you are getting by at that particular frequency. So on the Nyquist plot, the impedance can be represented as a vector or an arrow of length. This, you can see this modulus z. So the angle between this vector and the x-axis is nothing but your phase shift or a phase angle called phi. Now please remember, this Nyquist plots, they have one major shortcoming. So when you look at the data point, you cannot tell that what frequency was used to record that particular point. And always remember, the low frequency data are over here and the higher frequency data is on the left hand side. So lower frequency data is on the right hand side, whereas the higher frequency data is on the left hand side. So this is true for EIS data, where impedance usually falls as the frequency rises. Not true for all the circuits, but normally impedance usually falls as your frequency is rising. So the Nyquist plots the results from the equivalent circuit. So if you have a Nyquist plot which looks like this, then the corresponding equivalent circuit is somewhat like this. So another popular presentation method is known as the Bode plot. So the impedance is plotted in this case with log frequency, as you can see, log omega on the x-axis, and both the absolute value of impedance and the phase shift on the y-axis. So you see over here, you have the absolute value of impedance as well as you're also having the phase shift. Nyquist plot and the Bode plot, they represent the same results. Okay, you can actually express whatever this equivalent circuit thing either as a Nyquist plot or as a Bode plot. But unlike the Niki's plot, one thing which is very important is that this Bode plot, it explicitly it will show you the frequency information. Okay, you have an idea of the frequency because it is being plotted against logarithm of that frequency. So a small impedance in presence of large impedances, it can be identified easily using a Bode plot. So now let's look into the different electrical circuit elements, because what you will get from your EIS spectra is that spectra whatever I have shown, right? That Z double prime versus Z prime. But how will you fit it? So you need to know, you need to have an idea about the different electrical circuit elements. So now this in EIS data, as I said, is commonly analyzed by fitting it to an equivalent electrical circuit model. So now the common circuit elements are the resistors, capacitors, and inductors. So now you should know that how these generally behave. What is a resistor? The impedance of a resistor, you have to understand, is independent of frequency and it only has a real component. Because there is no imaginary impedance, the current through a resistor is always in phase with the voltage. Whereas in case of an inductor, what is happening? The impedance of this inductor, it is going to increase as the frequency increases. So inductor has only an imaginary impedance component. So the inductor's current is phase shifted 90 degrees with respect to the voltage. So remember, for a resistor, it is in phase with the voltage. Whereas in case of an inductor, the inductor's current is phase shifted by 90 degrees with respect to voltage. Another very important electrical circuit element is the capacitor. So the impedance versus frequency behavior of a capacitor is just the opposite to that of the inductor. So a capacitor's impedance, it decreases as the frequency is raised. So capacitors only have an imaginary impedance component, and the current through a capacitor is phase shifted minus 90 degrees with respect to the voltage. So now all these particular elements, how is it going to look, that we will see a little later. Another two elements which are very important that we will discuss in the, at first. So one is the Warburg impedance. This is given this particular sign. So please remember the different signs. For a resistor, it looks like this. If you have an inductor, the circuit element looks like this. For a capacitor, it looks like this. For Warburg impedance, a general impedance is which represents a resistance to mass transfer. So this is nothing but a general impedance which represents a resistance to mass transfer, that is diffusion control. The impedance, it depends on the frequency of the potential perturbation. At high frequency, the Warburg impedance is small since diffusing reactants don't have to move very far, whereas at low frequencies, the reactants have to diffuse further, and this increases the Warburg impedance. So on a Niki's plot, the Warburg impedance appears as a diagonal line with a slope of 45 degrees. So if I just go back, if you allow me to go back a little bit, if you look into the Niki's plots, which I showed right there in the beginning, you will see this particular line over here and the W written over there. So this basically is the Warburg element or the Warburg impedance element, which you see in a EIS spectra. And this particular is on the right hand side. So you know that this is in the lower frequency region. So now let's get back to whatever we were doing. That is, we are looking into the different circuit elements. So coming back to that, now we have another particular very important element, which is known as the constant phase element, and this is the symbol for it. So capacitors in EIS experiments often do not behave ideally. Instead, they act as a constant phase element. So this is a very general element which is used to model imperfect capacitors. So CPs normally exhibit a 80 to 90 degree phase shift. So please remember that when you're having an ideal capacitor, the phase shift what you see is 90 degrees. But whenever you are having a non-ideal capacitor, this phase shift is between 80 to 90. This is known as a constant phase element. So now let's see what are the different circuit elements and what are their impedance. So this equivalent elements for impedance, suppose you have a resistor, then for this case, this impedance is nothing but the resistance. In case of inductor, it is given as J omega L. This is the inductance. Then with the capacitor, this impedance value is 1 by J omega C, which is the capacitance. Is the capacitance over here. In case of Warburg impedance, this particular Z value or impedance value is 1 by Y0 root over JW. Whereas in case of CPE, you have this particular value. So the impedance value for each and every circuit element is given in this particular table. So now let's look into it. So what we have is basically very few of these electrochemical cells, it can be modeled using a single equivalent circuit. Instead, these EIS models, they usually consist of a number of elements in a network. So both series and parallel combination of these elements occur. So there are simple formulas. So if you have impedance in series like Z1, Z2, Z3, this is how the equivalent impedance is going to be. It is just going to be a simple addition of these impedance in series. Whereas if you have impedance in parallel, just like in resistors in parallel, you have to combine the Z equivalent like this. So resistance and impedance, you have to understand that both go up when resistors are combined in series, whereas impedance will go up, but capacitance will go down when the capacitors are connected in series. So these are a few points which you have to remember. So now let's see how your different circuit element is going to contribute when you are plotting it as Nyquist plot. So in Nyquist plot, as I said, the Z prime and Z double prime. Z prime is on the x-axis, which is the real axis. Z double prime is the imaginary axis. So, and this is in the y-axis. So if you have a resistor, then this resistance value is going to come right into the x-axis because resistance doesn't have any imaginary component to it. In case of a capacitor, it has only an imaginary component and the values are going to be coming only on the Z double prime axis. Whereas if you have a resistor and a capacitor in series, then in this case, this is how it is going to look. So it is going to have both a real component as well as an imaginary component, and along with it, you will also see a kind of a shift. So if you have a resistor and capacitor in parallel, which you mostly find in most of the circuits, in that particular case, this is how your Z prime versus Z double prime is going to look. You will find this particular kind of a plot over here. So if you have a simplified random cell, this is one of the most common cell model. So this includes a solution resistance, as you can see over here. Then it has a double layer capacitor, and then what happens is a charge transfer. So you have a double layer capacitor over here, you have a charge transfer over here, and then you have a solution resistance. And this is how your simplified random cell is going to look when you are drawing the equivalent circuit. So common equivalent circuit models is one of the most common ones you will find. So you have this semi-cycle Nyquist plot coming because of this particular cell structure. You will find that on the left-hand side of it, what you have, this is basically the high frequency area, and you will find this semicircle actually cutting over this Z prime line. And so this basically tells you that there is a resistance, which is inbuilt resistance in this particular cell, whatever you are having. And along with it, this particular thing is telling you the charge transfer resistance, which is happening. So this R omega and this RCT can be directly found from the Nyquist plot. And the capacitance can be calculated by the value at the peak of the semicircle. So this is how basically this entire thing looks like. You can solve these particular equations and you will see how basically the Z prime versus Z double prime plot is going to look. So then sometimes you can have mixed kinetic and diffusion control. So consider cell process is controlled by both charge transfer as well as mass transfer. So with charge transfer, we have already seen how it is going to look because this is just simple charge transfer. Now what is going to happen if you also have a mass transfer or a diffusion happening? So in that particular case, you have two cases. One, when your frequency is very small. In that case, what you have is this particular plot Z prime versus Z double prime is nothing but the equation of a straight line. And this is how it is going to look. Whereas when your omega value or your frequency is very high, in that case, this particular plot looks exactly like the charge transfer plot. So in all, what does it mean? So that means when your frequency is less, in that case, what you have is a straight line. That is what you see over here. That is the Warburg impedance kind of line. Whereas when you are having the frequency to be very high, in that case, it is only charge transfer what is happening. And so that is why over here, your this entire, so in this particular case, this is looking just like charge. So one thing to remember from this plot is that when your frequency is very high, what you have is the charge transfer process, it dominates. When the frequency is very less, then the diffusion process, it dominates. So combining these two, we therefore get the Nyquist plot. At high frequency rate, cell process is determined by charge transfer. At low frequency rate, cell process is determined by mass transfer or diffusion. And in the intermediate region, you will find a combination of both what is happening. So now you come to EIS modeling. So electrochemical cells can be modeled as a network of passive electrical current elements. The network is called the equivalent circuit. And the EIS response of an equivalent circuit can be calculated and compared to the actual EIS response of the electrochemical cell. So how is the modeling? How can you do this modeling? So the process is you will get the experimental data. Then you will develop a possible equivalent circuit. Then you will adjust it until it fits well. The parameters related to different elements you will obtain from that model. And the common softwares which are used for it, these are the ZSynWin, or you can have ZView, or you can have the Gamry Echem Analyst. So these are the three different common software which are used to actually analyze your EIS spectra, which is obtained experimentally. So ideal spectrum with electrical circuit elements, how it is going to look. So with the decreasing frequency, so you remember on the left hand side we have the highest frequency and on the right hand side we have the lowest frequency. So with decreasing frequency, the first feature is a non-zero ohmic resistance where the spectrum intersects with the real Z prime axis. At high frequency, it is represented in the equivalent circuit by a resistor RHF. So this is how this is going to look. Followed by something what you have over here. This is RHF plus this R value. So for every of this semicircle, you have one more circuit coming up where you are having a resistor and a capacitance in parallel. So this is how your equivalent circuit, and this particular line is because of your Warburg impedance, and this is shown over here. So an ideal spectrum, it should look like this, that you have these semicircles and then you have this particular straight line. But when you look actually into a lithium-ion battery cell, when you have your this EI spectra coming in, it looks somewhat like this. Okay, so these semicircles are not complete. So before it can complete, you have this another semicircle coming in, and then you have this straight line. So this is basically what are the different processes which are going on in your cell. So internal dynamic phenomena and the corresponding Nichols plot of this lithium-ion battery. This is shown over here. So lithium-ion migration through the solid electrolyte interface layer, activation kinetics in both negative and positive electrodes, double layer effects at the interface of electrolytes, and lithium-ion diffusion processes in the active material of the electrode. So these are the 4 different things which are happening when your cell is cycling. Okay. So, and with this plot, when you are having this particular EIS spectrum being generated, this is the equivalent circuit. And when you fit to it, you will get all these different values, that what is the resistance of the cell, what is the resistance of the SCI layer, what is the resistance of charge transfer you are seeing, and how these different processes are changing as per your cycling. And as per your cycling, that's when you're charging and discharging the cell. So now you have these different regions over here. You have this region A where you see this first line which is intersecting the Z prime. So region A is represented by a single ohmic resistance. This area corresponds to the battery ohmic losses, including the resistance of the current collector, active material, electrolyte, and separator. So this you can say that this particular resistance is nothing. This resistance is basically arising due to the different components of your particular cell. Then you have a high frequency region which is B, and this can be represented by the solid electrolyte interface resistance or RSEI, SEI layer capacitance, and the fractional element which is delta alpha 1 corresponding to the lithium ion migration through the SEI film layer. So you have this SEI film formation, and for this again you have this entire equivalent circuit which is going to correspond to this particular plot of your Z prime versus Z double prime. Then you have a medium frequency region. This is the C. This is where you can see that actually the larger semicircle which is happening. And this is represented by the charge transfer resistance which is happening, a double layer capacitance, and a fractional element delta alpha 2 which corresponds to the activation kinetics and double layer effects at the interface of the electrolytes. And then of course after that what you have is a low frequency region D. This is represented by a Warburg element and a fractional element corresponding to lithium ion diffusion process in the active material of the electrodes. So you see each region. So here you have one resistance which is coming due to different components of your cell. This particular equivalent circuit diagram is because of the SCI layer formation. Then this again is coming in, this particular thing, this is coming in because of the charge transfer. And this diffusion, whatever you see, this gives rise to this Warburg impedance. So EIS modeling of a lithium-ion battery becomes very easy when you are able to fit this to the equivalent circuit and you get the different values. And then accordingly, you can see that whether the resistance is increasing or impedance is increasing or decreasing whenever you are changing the electrolyte or you are changing, your electrode material, what are the different stages, whatever is happening. So in situ, you can find out the dynamic processes which are going inside the cell. Now coming to battery life. So how you can extend the battery life? You have a battery, now how you can extend the battery life? So you have to understand that most lithium-ion batteries should not be charged at ambient temperatures below 0 degrees centigrade or above 45 to 50 degrees centigrade. In that case, what you are going to do is you are going to bring down the lifetime of your battery. So charging at high temperature will decrease cycle life and it may present a safety hazard. Charging at low temperatures may lead to growth of lithium metal dendrites, which can result in an internal short circuit, destroying the battery and potentially causing fire. Also, you have to remember the battery should be stored at or near room temperature and at 20 to 40% state of charge. For a lithium-ion battery, the charging, it shouldn't be drained. It shouldn't be completely drained. The ideal is that it should have 20 to 40% state of charge. Storage while fully charged or in elevated temperature should be avoided, as this will put stress on the cell, because when it's fully charged, what you are doing, you are actually pushing all the lithium ions from the cathode, however can be moved into the anode. So that is a kind of a stress level of the cell is going to increase. So it reduces the battery life and it increases the amount of energy which will be available for thermal runaway should an accident. So these are few safety points you have to keep in mind to extend your battery life. Now, as I discussed, energy density versus power density. Energy density is the amount of energy in a given mass or volume, and power density is the amount of power in a given mass. So you have to understand batteries, they have a higher energy density than capacitors, but a capacitor, it has a higher power density than a battery. So the difference comes from batteries being able to store more energy, but capacitors can give off energy more quickly. So if you have this particular plot of power density versus energy density, if you remember very clearly, I had discussed the Ragon plot in the previous lectures. So this is a plot which is used for comparing energy density of various energy storing devices. On such a chart, the values of specific energy in watt-hour per kg are plotted versus specific power, which is watt per kg. Both axes are logarithmic, which allows comparing performance of very different devices. So if you see over here, you have lithium-ion battery, which is having a comparable energy density and power density. Power density is less and energy density is also good. But there are two other things which definitely gives you more power density and the other gives you more energy density. One is the capacitors, which give you more power density, whereas on the other side, extreme side, you have fuel cells, which give you more energy density. Since we have discussed batteries extensively, now we will be discussing these other two energy storage devices which you find on the Ragon plot. One is your capacitor and the other is your fuel cell. So first we will be discussing the supercapacitors. So what is the history of supercapacitors? So supercapacitance is basically storing of charge between an electric double layer. So the electric double layer capacitor effect was first noticed in 1957 by the scientists working in General Electric. The Standard Oil of Ohio rediscovered this effect in 1966 and they gave licensing to NEC, which in 1978 marketed the product as a supercapacitor. So if you look into the global supercapacitor market size, right from the 2000s to 2020, you see this exponential increase what has happened. So in hundreds of millions of dollars, the supercapacitor industry has grown, and obviously something which has so much amount of potential application commercially, then definitely a lot of research is going on in this particular area. So what is supercapacitor? You have heard of capacitors, right? So what is the principle of capacitor? So you have a dielectric material in between conductive plates whose area suppose is A, and this capacitance is nothing but a ratio of the stored charge by voltage. So this can also be given when you are talking about a capacitor like this, where C is equal to epsilon R, epsilon 0 A by D. What is A? A is the area of these conductive plates. ER is the relative static permittivity or the dielectric constant. E0 is the permittivity of free space, the value of which you know all theoretically. And D is the distance between these two storage plates. So what is the energy? This is the capacitance value. So what is the energy stored in the capacitor? It's half CV square. And what is the power which can be delivered per unit time? This is V square by by 4 ESR, and ESR is nothing but the equivalent series resistance. Okay. So it's V square by 4 of the 4 times the equivalent series resistance. This is the power. So what are electrochemical capacitors? In these kind of capacitors, the charging and the discharging, they occur at the electrode-electrolyte interface of high surface area materials such as porous carbon or metal oxides. There is a rapid storage and release of energy. So in this particular case, if you have cell potential, which is plotted versus time, you can see that this is how the cell potential is going to drop off, and then also it is going to increase. And of course, the equivalent series resistance gives rise to this voltage drop over here, as you can see. So what are supercapacitors? So capacitors we discussed. So what are supercapacitors? So this energy storage in supercapacitors is mainly in the interface between electrode and electrolyte. This energy storage method has a great relationship with the electrode materials used. So what you do over here is you are storing electrical energy through the electric double layer capacitance formed by the charge separation on the interface between electrolyte and the path solution. So you have these polarizing electrodes over here, you have a collector, and then you have an electrolyte, and this electric double layer is getting formed. So the supercapacitors, it can achieve higher capacitance because of thinner dielectric and higher surface area of electrodes. So in this particular case, you need to have the D should be less, the A should be more, and obviously your capacitance is going to increase. So supercapacitors compared to capacitors, they have a larger area for storing more charge with capacitance in the range of farads, and they store more energy than electrolytic capacitors. So they have a very low leakage current. They are suitable for many applications that can operate in the 1.8 volt to 2.5 volt range. And the life of a supercapacitor is around 10 to 20 years. And though the capacity could be reduced from 100% to 80% after about 8 to 10 years, but still it will function, but definitely the capacity is going to be less. So how we can define? So you have capacitors over here. This is how, with the dielectric material and your electrode plates. Whereas in case of supercapacitors, as you can see over here, the surface area is increased, your D value is decreased, so your capacitance increases manifold. So if you look into the taxonomy of supercapacitors, so you have these different types. One is the electrochemical double layer capacitor. So electrostatic, what is the mechanism? In this case, electrostatically ion adsorption or desorption at the interface of the electrode or the electrolyte takes place. Other thing what you have is the pseudocapacitors. In this case, what you have is a reversible Faradaic redox reaction between electrolyte ions and the electroactive elements. So this is a Faradaic process. Electrochemical double layer capacitor is a non-Faradaic process. It generally works via adsorption-desorption at the interface of your electrode and electrolyte. And then what you have is a hybrid capacitor. So in this case, it is an electrochemical double layer ion adsorption-desorption along with a reversible Faradaic reaction. So as the name suggests, it is hybrid between an electrochemical double layer capacitor and a pseudocapacitor. So a hybrid between capacitors which work via Faradaic process and capacitors which work via a non-Faradaic process. So these are the hybrid capacitors. This is a taxonomy of capacitors, supercapacitors. So now let's look into the charge storage system. Electrochemical double layer capacitors, they store energy using ion adsorption, so there is no Faradaic or redox reaction happening. You have a high specific surface area of the electrodes, and generally carbon is used. And you have a Helmholtz double layer, which states that two oppositely charged layers form an electrode-electrolyte interface, and they are separated by atomic distance. And this Guy-Chapman model recognizes two regions of this ion distribution. You have an inner region, which is the Stern layer, and then you have a diffuse layer. So this entire double layer is basically a combination of your Helmholtz layer or the Stern layer as well as the diffusion layer. And you know, this capacitance, it depends on the type of electrolyte you have used. If you use an aqueous electrolyte, you get the capacitance around 150 to 300 farads per gram. Whereas if you use a non-aqueous electrolyte, you can get a capacitance of 100 to 120 farads per gram. So these are the different electrolytes and their cost and toxicity and ionic size. This table you can go on later at leisure. So what is the salient feature of the electrolytes and electrodes? In the aqueous electrolyte, you can have sulfuric acid, you can have potassium hydroxide, you can have an acidic electrolyte, or you can have an alkaline electrolyte. These are generally low cost. They have higher ionic conductivity. They have a low potential window of around 1.23 volts. And the problem is that the acid alkali corrodes the current collectors. So an important consideration when selecting an electrolyte for porous material is the size of the electrolyte ion and whether they will be able to access the electrode porosity. You also have to understand whether, you know, this whatever you are selecting as electrolyte, whether the ions are going to be able to pass through that pores, whatever is there in the electrode surface. In case of non-aqueous electrolyte, what is happening? You have a higher operating voltage, which is a plus point. It has a moderate cost, but it has a lower ionic conductivity. So that is a problem. So if you have these different electrodes, you can have activated carbon, templated carbon, you can have carbon nanotubes, you can have carbide derived carbon, you can have carbon black, aerogels. Along with it, you can have these different kinds of electrolytes. You can have aqueous electrolyte, organic electrolyte, or you can have ionic liquids as electrolytes, and different surface area, as you can see. What you will see that the capacitance value changes. So if you have an activated carbon with a surface area of 1000 to 3000, in presence of an aqueous electrolyte, the capacitance is 200 to 400 farads per gram. Whereas if you have a templated carbon where the surface area is considerably less, but you still have an aqueous electrolyte, you see the capacitance has come down drastically. It is now 120 to 350 farads per gram. So similarly, all these different values are given. So using this different permutation combination, you can find out the kind of supercapacitor you are going to develop. So now, what is pseudocapacitance? Pseudocapacitive electrochemical capacitors, what they are? So some materials utilize fast and reversible redox reactions at their surface. So this represents a different kinds of capacitance contribution to double layer capacitance. This capacitance is quite significant, is not electrostatic in origin, and occurs when an electrochemical charge transfer process takes place to an extent limited by a finite amount of active material or available surface. So what are the different kinds of pseudocapacitive elements you can think about? One is the family of the conducting polymers such as polyaniline, polypyrrole, or derivatives of polythiophene. And the most commonly investigated class of pseudocapacitive materials, these are the transition metal oxides like ruthenium oxide, manganese oxide, lead dioxide, nickel oxide, ferric oxide, etc. And porous carbons that possess a significant proportion of heteroatoms or surface functionalities can also contain a pseudocapacitive component in their overall capacitance. So while double layer capacitors store energy on the surface of the materials, electrochemical capacitors store charge throughout the entire volume and via fast doping dedoping exchange of ions, and hence the amount of energy that can be stored with electrochemical capacitors is generally higher than that with the EDLC type of materials. Always remember the Faraday reactions, they suffer a lower self-discharge. So that is a plus point of these particular pseudocapacitive electrochemical capacitors. So pseudocapacitors, they store energy using fast surface redox reactions. Redox reactions occur at the surface of the active material. As I said, it can be metal oxides, ruthenium oxide, ferric oxide, manganese oxide. And you can also have conducting polymers like polyaniline, polypyrrole, polythene. So metal, polythiophene, etc. Metal oxides, the capacity is going to be like around 1300 farads per gram in case of ruthenium oxide with a nominal voltage of 1.2 volt. Whereas in case of conducting polymers, the capacity is around 30 to 40 milliampere hour per gram and the nominal voltage of around 1 volt. So 1 molar H2SO4 aqueous electrolyte is used, and that gives a specific capacitance of around 734 farads per gram. So this is how it's going to look. You are having an electrolyte, which is 1 molar H2SO4. You have this ruthenium oxide as the main over here, and then the reaction which is happening, and this is the maximum capacitance you are going to get. So we also work a lot on these kind of materials, and as you can see over here, I have shown you one particular example where you have a bismuth oxide which is being used as a supercapacitor, or which is deposited on polyaniline composite electrodes. And this shows a very extended voltage window. The voltage window it increases means definitely your application is more. So this kind of devices, with the small LEDs where you can light up, this is possible using these kind of supercapacitor cells. So there is another class which is known as an asymmetric capacitor, asymmetric electrochemical capacitor. So this consists of two dissimilar electrodes, and that is why it is known as a hybrid supercapacitor. So we had EDLC, we had pseudocapacitor. Now what we have are two dissimilar electrodes, and this is a hybrid supercapacitor. So electrodes are what? One is the EDLC type, which is absorption type, and the other is the pseudocapacitor type. So where basically the Faradaic reactions are taking place. So the Faradaic and the non-Faradaic electrodes should be selected with high charge discharge rate capability. So that's a very important point when you are trying to develop these kind of supercapacitors. The Faradaic and the non-Faradaic electrodes should be selected such that their potentials are close to either the low or the high end of the operating potential window, which will maximize the operational voltage and energy density of this asymmetric cell. So as the Faradaic electrodes exhibit a much higher specific capacitance than the non-Faradaic electrode, this mismatch can be compensated gravimetrically by balancing the active mass of the two electrodes, usually by using a thicker, denser non-Faradaic electrode. So please remember that whenever we are having a Faradaic and a non-Faradaic electrode, so if you have a much higher specific capacitance, which you will find obviously for Faradaic electrodes, then the non-Faradaic component, you have to make it more thick. so that by the gravimetric balance, it is able to balance so this mismatch can be compensated. And the non-Faradaic electrode should have the highest possible electronic conductivity, surface area, and porosity. So now if we look into the charge and discharge pattern of a battery, it looks somewhat like this. Whereas charge and discharge pattern in case of a double layer capacitor, it goes like this. The charge and discharge, you will see there's a severe voltage drop. So if you look into the difference between electrochemical capacitor and battery, the charge time in case of a capacitor, 70% charge happens within seconds, whereas in a battery, generally for charging a battery takes hours. The discharge time for an electrochemical capacitor is very short, whereas in case of a battery, it is long. The charge discharge cycles goes from 10,000 to almost 10 lakhs in case of capacitor, whereas for a battery, 1,000 cycles to 2,000 cycles is good enough. Pollutants, in case of electrochemical capacitor, there is none, whereas in case of battery, there is quite a few. There's the metals which are there, which can be, they can be hazardous. So if we are looking into supercapacitor and battery, the supercapacitor can be considered, like you have this 100-meter race where you require a burst of power, whereas the battery, if you see, it is like a marathon, running a marathon. So it will give you, continuously, it is going to give you energy, but it's going to give you for a very long period of time. What are the different applications of supercapacitors? It is definitely used for backup for uninterruptible power supplies. Then lightweight power supplies for small aircrafts. It provides short duration power for various vehicle systems such as braking or steering. It is used to absorb power during short periods of generation such as regenerative braking. And then it extends the range and battery life in hybrid electric vehicles. So these are the different applications for supercapacitors. So these hybrid electric vehicles have also come up. The CSIRO in Australia, which is the National Space Agency, they have developed the Ultra battery, which combines a supercapacitor and a lead acid battery in a single unit. So it has a 4 times longer life cycle, 50% more power, 70% cheaper than the battery which are normally used in the electric vehicle market. So coming to now the last part of our energy storage materials, which is the fuel cells. So what is the fuel cell? As I said that the capacitors, as I said, the power density is very high. In case of battery, we have an optimum of energy density and power density. Neither of them are too high or too low. But in case of fuel cell, what you have is something which has a very high energy density. So fuel cell is an electrochemical device that converts chemicals such as hydrogen and oxygen into water, and it produces electricity in the process. So theoretically, as long as the reactants, that hydrogen and oxygen, are supplied to the fuel cell, it will continually produce electricity and never go dead, unlike conventional batteries. So if you have a fuel cell stack, so then what you have is the cathode and the anode. From the anode part, hydrogen is moving in the cathode part, oxygen is moving in. You have an electrolyte in a matrix, and ultimately you have generation of electricity, and the byproduct is only water. So as long as you have the reactants going in, it will continuously give you power. It will always give you electricity. So this is how basically you have this fuel cell stack at fuel processing and power conditioning happening in case of fuel cell. So a fuel cell, it uses the chemical energy of hydrogen or other fuels to produce electricity in a clean and efficient way. So if hydrogen is the fuel, the only product is nothing but electricity, water, and heat. So what are the advantages? Obviously, you have reduced greenhouse gas emission. You have reduced oil consumption. You have expanded use of renewable power. Why? Through the use of hydrogen derived from renewable resources as a transportation fuel, as well as for energy storage and transmission. Then you have a very highly efficient energy conversion. You have fuel flexibility. You can use diverse domestic fuels, including hydrogen, natural gas, biogas, and methanol in fuel cell. They generally, that the name of the fuel cell differs as per the fuel whichever you are using. Normally, fuel cell, it is hydrogen and oxygen, but you can also use diverse fuels like domestic fuels. You can use hydrogen, you can use natural gas, you can use biogas as well as methanol. And obviously, it has much reduced air pollution. Why? Because it is giving you as a byproduct only water. Then you have, there is no criteria pollutants which are coming into the picture here, and you have water use, and it's a highly reliable grid circuit. Fuel cells also have numerous advantages that make them appealing for end users, including quiet operation, low maintenance needs, and very high reliability. What are the basics of the fuel cell? So fuel cell, they will convert the chemical energy directly into electrical energy. So what is the difference with batteries? Fuel cells require a fuel to flow in order to produce electricity. And heat is produced from chemical reaction, we have to remember, and not from combustion. So there are different types of fuel cells. So there can be a proton exchange membrane fuel cell. You can have a direct methanol fuel cell. You can have an alkaline fuel cell. You can have a phosphoric acid fuel cell, molten carbonate fuel cell, or a solid oxide fuel cell. So the ones which are marked with star, that is a phosphoric acid fuel cell or a molten carbonate fuel cell or a solid oxide fuel cell, these are all suitable for microgrids. Okay. But for microgrids, you can use this. The others can be actually used for national level grid supply to store the energy. So the fuel cell types, now again, we will see what are the differences. So hydrogen fuel cells. So which are the ones which are using hydrogen fuel cells among all these different fuel cells I discussed earlier? One is the proton exchange membrane fuel cell. In short form, it is known as PEMFC. Then you have AFC, which is nothing but the alkaline fuel cell. That also is a hydrogen fuel cell. The alkaline fuel cell is because of the electrolyte, whatever you are using. Then you have a PAFC, which is a phosphoric acid fuel cell. This is also a hydrogen fuel cell. And along with it, you have the molten carbonate fuel cell and also the solid oxide fuel cells, which is MCFC and SOFC respectively. Okay, so these all are using hydrogen fuel cells. So basically using hydrogen as a fuel. And then you can have hydrocarbon fuel cell where hydrocarbon is used as a fuel. So you have this direct methanol fuel cell or DMFC. You can have direct ethanol fuel cell or DEFC. Or also you can also have DFAs, which are another different kinds of this hydrocarbon fuel cell. Then you can also have biofuel cell, that is MFC, which is known as the fuel cell where you can using biofuels, or else you can also have EFCs. So how are this entire fuel cell assembled? So if you look over here, what you have is basically some kind of these, the electrodes you have over here. Then you have a gas diffusion layer. Then what you have is a catalyst layer. And then what you have is a membrane. So what is this catalyst layer, which is in between the gas diffusion layer and the membrane? So at the interface of the membrane, there are the layers with catalyst particles. Platinum catalyst is supported on carbon particles. So this is the catalyst layer. What is the gas diffusion layer? The polymer membrane with catalyst layer settled on the two sides is sandwiched between two sheets of porous layers, which are known as the gas diffusion layers. So these are generally made out of carbon cloth or carbon fiber paper. It allows diffusion of both the reactant gases and product water. So gas diffusion layers also perform as the electrically conducting electrodes and the heat conducting mediums. So the membranes, these this catalyst layer and the gas diffusion layer, they are usually combined together as the membrane electrode assembly. So if you look into the fuel cell operation, let's see how it is moving around. So this what we are discussing is the proton exchange membrane fuel cell. So what happens is the hydrogen atoms, electrons and protons, these are separated at the anode. So you are having over here the anode, hydrogen is moving in. What you're seeing is the proton is getting separated. It is moving through this membrane because it is a proton exchange membrane. So only the protons can go through the membrane. That is why it's known as a proton exchange membrane fuel cell. On the other side, you're having this oxygen coming in. This oxygen then reacts with this proton along with the electrons and it forms water. So the ultimate reaction is oxygen reacting with hydrogen giving you water. And this is definitely the potential of it, which is 1.23 volts. And the byproduct for this particular reaction is nothing but water. So this is how basically the fuel cell operates. Always in a cell, you will find there is a voltage loss is happening. And this difference between the ideal voltage and the real open circuit voltage is caused by factors such as crossover of the reactants. In some cases, what is happening is some of the hydrogen and oxygen, they are simply crossing over and the reaction is not happening. And so obviously the voltage is not high enough, it is dropping and you see an open circuit voltage which is less than the ideal voltage. But then if you look into the voltage versus current density curve, this curve over here, as you can see over here, this particular gray line over here, this curve which characterizes the relationship between the voltage and the current, this is known as the polarization curve. And as you can see over here, it is not a constant one. An open circuit voltage is constant, but the polarization curve looks like this.
And this is because of the various losses which are happening, loss in the voltage which is happening due to the various processes which are occurring in this particular cell. So what are these different losses? The one in red I have marked is the activation loss. And this part of voltage is lost in driving the chemical reaction. So to activate your electrode, this is the particular voltage which is needed. And so this is lost. So these losses depend on the catalyst material and the microstructure of your membrane exchange assembly, reactant activities, and on the current density. So these are the activation losses. Then you have something in blue which is decreasing constantly, and this is known as the ohmic loss. So this decreases constantly with the current density. This is voltage loss which is caused by the resistance associated to the electrodes, the electrolyte, and other interconnections. Ohmic losses, these are proportional to the current density. Besides the material and the structure of the fuel cell and the temperature, this can all impact these kind of losses. So ohmic losses are impacted by the material, the structure of the fuel cell, and also by the temperature. Then at last, that orange color thing is known as concentration loss, and this generally you find at very high density, current density. So these losses, they result from the drop in concentration of the reactant at the surface of the electrodes, and they depend strongly on the current density, reactant activity, and also on the electrode structure. So this is what you have over here in a nutshell. So you have these different kinds of cell values over here, the cell abbreviations given over here. This is phosphoric acid fuel cell, and this is your MCFC, this is DMFC. So accordingly, you have these different fuels. You have hydrogen and carbon monoxide. You can have hydrogen only. You can have methanol and water. You can have only hydrogen. The oxidizer can be oxygen, it can be carbon dioxide, but mostly it is oxygen. And the electrolyte can be a solid oxide ceramic electrolyte. It can be a molten carbon salt in case of MCFC. It can be potassium hydroxide in case of the alkaline fuel cells, short form is AFC. Then you can have phosphoric acids as the electrolyte in case of PAFC. Perfluorosulfonic acid membrane is used in case of DMFC, and perfluorosulfonic acid membrane is also used in case of PEMFC, which is proton exchange membrane fuel cell. So now let's look into the operating conditions. So please remember, all these cells, they don't function at all different temperatures. If you see over here, I have marked over here. So most of them, like PEMFC, DMFC, they all work from between room temperature to 100 degrees centigrade. This phosphoric acid fuel cell, it goes up to a higher temperature from 150 to 220 degrees centigrade. This alkaline fuel cell goes up to 250 degrees centigrade. In case of MCFC or molten carbon salt, good research is going on. And in this case, you can see the temperature is around 600 degrees centigrade, whereas SOFT or solid oxide ceramic electrolytes, in this particular cell, the temperature is going to be around 1000 degrees centigrade. Okay, so this is how it is given. So direct methanol fuel cell, as you can see, it operates best at 60 to 90 degrees. The methanol is fuel, and this is normally used for portable electronic devices. Whereas if you see the alkaline fuel cell, this is the fuel cell which has been used in Apollo missions. Then proton exchange membrane fuel cell, this was originally developed by General Electric for space applications. Phosphoric acid fuel cell, it is used for stationary energy storage devices, so where you can actually use these cells for grid level energy storage. Then molten carbonate fuel cell is a hydrocarbon fuel reformed in situ. So if you have this proton exchange membrane fuel cell, the electrodes, that is the anode and the cathode, they are separated by a polymer membrane electrolyte. Each of the electrodes is coated on one side with a thin platinum catalyst layer. The electrodes, catalyst, and the membrane, together they form the membrane assembly. Hydrogen and air are supplied on either side through channels formed in the flow field plates. We look into the fuel cell operation in case of a solid oxide fuel cell. This is given very nicely pictorially over here. So you have a cathode and anode and the electrolyte, which is sandwiched between the two. Then oxygen from the air, as you can see, is flowing through the cathode. A fuel gas containing hydrogen, such as methane, it flows past the anode, and you can see over here using the steam, then this kind of reduction is taking place, and ultimately hydrogen is formed, and this hydrogen is permeating through the anode. So oxygen ions migrate through the electrolyte, and they react with this hydrogen to form water. Water reacts with the methane fuel to form carbon dioxide and hydrogen, as you can see over here. Electrons from the electrochemical reactions flow from the anode to the cathode through an external load, and this is how basically your current or the electricity is generated. So what are the advantages of fuel cell? It has a very high efficiency, it is modular, it is quiet, it is non-polluting, It can be distributed, in different regions. So you can put in, different kinds can be put in microgrids. It combines heat and power, and it is load flexible. So fuel cells using methanol and oxygen are being developed. Fuel cells are used extensively in the space program as the sources of DC power. They are very efficient, capable of providing hundreds of kilowatts of power. So what are the different applications? It can be used as power sources in remote areas. It can be used to provide off-grid power supplies. It can be applicable in both hybrid as well as electric vehicles. It can be used for wastewater treatment plant and for landfills, cellular phone, laptops, and computers. Then it is used for hospitals, credit card centers, and police stations, buses, cars, planes, boats, forklifts, trains, vacuum cleaners. So all these fuel cells can be applied as energy storage devices for all these different applications. So you can have stationary power systems, you can have transportation applications, you can have portable fuel cells, you can have space applications. So these are classification of application areas of the fuel cell. So with this today, I will be ending the entire syllabus, which is for your energy storage materials. In the next class, which is going to be on Monday, we will talk about magnetic materials.